So the following is a presentation I had to make for a course I took recently on algebraic number theory. And the title, How to Join the Society of p-adicts, is inspired by the shirt that I recently purchased, where we see the symbol QP here. And at the end of the talk, I'm going to show you the reverse side of this shirt. And I'll put a link as to where you can purchase it, but more or less the goal of the talk is to explain some of the things on the reverse of the shirt. So, towards that end, we're going to be talking about defining the p-adic numbers. So this will start off with a discussion of the idea of Archimedean versus non-Archimedean norms, which will then lead us into analysis and topology of number fields. In here, we'll be looking at, in particular, the definition of the p-adic numbers. Then we're going to turn things back around towards some more algebra, and at the end, I'll just spew some general nonsense I had planned as some just bonus for the end of my talk. Okay, so first, we just recall the definition of an absolute value. Now we're defining it for an arbitrary field, but this is just formalizing the intuition of our normal absolute value of a real number. So it's multiplicative, satisfies the triangle inequality, and it's, well, positive except precisely for the additive identity.
Recall that for any element of our field, that element generates a fractional ideal. And that fractional ideal has a unique decomposition into prime ideals. So this is just a decomposition of prime ideals in a numerator and prime ideals in a denominator. So in other words, So recall that for some element of our field, we get a fractional ideal. And this fractional ideal belongs to, well, the collection of all fractional ideals of the ring of integers. And this is really just indexed by all the So recall that the divisor ring of our ring of integers, or the ring of fractional ideals, well, is just that. It's a ring of fractional ideals, which one can think of just Q direct sums of the integers. So in other words, it's some vector of integers indexed by the prime ideals of our ring of integers. And so given any element in our fields, that will generate a fractional ideal for us. And we're going to define v sub p of a to be the projection of the pth coordinate. In other words, it's the number of times that the prime ideal p appears in the decomposition of the fractional ideal generated by a. So of course this will be positive if the ideal appears a positive number of times, 0 if it doesn't appear at all, and of course it will be a negative integer depending on how many times it appears in the quote-unquote denominator of the fractional ideal. So then we're going to define the p-adic norm as being, so n of p here, recall this is the numerical norm. So this is simply the size of the finite quotient ring, which is the ring of integers modulo the prime ideal p. So n of p is that cardinality, and we're going to put it to the negative of this v sub p of a. So specializing to the case of the rational numbers, we're just going to write, instead of the parentheses around the p, since our prime ideals are precisely generated by the prime numbers. We're just going to denote it with a p and drop the parentheses, and we're going to call this the p-adic absolute value. So in particular, suppose we have some rational number, and we've factored out the largest divisor of p from the numerator and denominator. So we have some number of this form, p to the power of m, times r over s, where r and s are both prime to p. Then the p-adic valuation of this is simply going to be p to the minus m.
So if we have an absolute value on a given field, we say it's non-Archimedean if it satisfies this stronger version of the triangle inequality. And in fact, we're going to get something even stronger just out of this definition. So in the case that x and y do not have equal norm, then we can we rewrite the norm of x as the norm of x plus y minus y. And then by our assumption that we're working with a non-Archimedean norm, that's going to be at most the maximum of the norm of x plus y and the norm of y. Well, the norm of x plus y, that's at most the maximum of the norm of x and the norm of y. But we're assuming in this case that it's x, which is the maximum. So now if we look at all these inequalities, everything gets sandwiched together. And in particular, we find that the norm of x plus y is equal to the norm of x on the nose. So in fact, when x and y are not of equal norm, for a non-Archimedean norm, we actually have equality in the definition. So the reason why this is called Archimedean versus non-Archimedean is, of course, Archimedes, in one of his texts, he put forward this argument, said if you got two sticks of different lengths, and you stack up enough sticks of length A beside the one stick of length B, eventually, if you've got enough sticks, though that succession of smaller sticks, total length will overtake the length of B. And in our case, well, we say more formally the Archimedean property of the real numbers says that for any pair of real numbers, if A is less than B, then there's some n such that A times n is greater than B. So, of course, this holds for the real numbers, and in particular, if we augment this a bit to talk about the norm of A versus the norm of B. But now let's consider a norm which is non-Archimedean on some number field, and we consider some integer multiple of an element of, any field. Then, by assumption, that's at most the maximum of the norm of x and the norm of n minus 1 times x. But the norm of n minus 1 times x, that's going to be the maximum of x and the norm of n minus 2 times x. And so on. Until eventually we're just going to get this nested stack of maximums. And that means, well, the maximum of the norm of x and the norm of x is just the norm of x. And so the norm of x is going to percolate back up through the stack, and we're going to find that this is still just equal to the norm of x. So we find, in particular, the Archimedean property is not satisfied for non-Archimedean norms, so it's a pretty apt name. Okay, so an absolute value, it turns out, this property we just talked about, it turns out that it's actually characteristic of non-Archimedean norms. So if we have if we form the set of all integer multiples of the identity of a field, if the non-Archimedean norm, or I should say if the norm is bounded on that set, then it will be non-Archimedean in return. So if we think about the p-adic norm that we defined for prime numbers, and we take the largest factorization of p out of some integer, so it becomes p to the n times m. Then the p-adic evaluation of that is p to the minus n, and that's strictly less than 1. So certainly for any integer multiple of the identity in the rational numbers, this property is true, and we see that then, in fact, yes, these p-adic norms are, in fact, non-Archimedean. Okay, so whenever you have a norm, then we also get a very natural metric coming from that norm. We simply set the metric, well, first, a review of what it means to be a metric. That is, the distance from x to y is 0 if and only if the components are equal. Of course, it's symmetric, and it also satisfies a triangle inequality. So we can define now a metric in terms of our norm by simply setting the metric dxy to the absolute value of x minus y. And of course, now that we're talking about metrics, that means we have, in particular, metric spaces. It makes sense to talk about balls of radius epsilon, and in particular, we can generate a topology. Well, it turns out that there's actually a nice sort of algebraic, if you will, characterization of when two norms, even though they may differ on the values they take, when they define the same topology on a field. And in particular here we see that it's when one can be written as the positive power of another. So we're going to skip this proof, but it does appear I do write it up in detail in my notes for this series. So suppose we had two integers, p and q, they weren't equal, and the p-adic evaluation at p is p to the minus 1, of course, which is strictly less than 1. But the q-adic evaluation of p is just going to be q to the 0, because these are distinct primes, so they're not going to appear in each other's prime factorization, of course. And so if one of them is 1 and the other is less than 1, then certainly no positive power is going to do anything to make that 1 equivalent to some number less than 1. So, in fact, we find that for any distinct primes, the p-adic, or p and q, I should say, the p-adic and q-adic norms are topologically distinct, not just distinct in their values. So, now we come to a pretty weird feature that I think is a really exciting fact about the p-adic metric on the rational numbers. Let's consider, of course, we could have an equilateral triangle. So by this I mean one could imagine taking a rational plane and picking 3 points x, y, z in that rational plane and going to measure the distances between them. Well, if it's equilateral, then certainly two sides are the same. But if it's not equilateral, then two sides must differ. So without loss of generality, we say the side x minus y and the side y minus z. So then x minus z can be rewritten as x minus y plus y minus z. And that's going to be equal to, on the nose, by one of our previous observations. So now, before we get on with developing the theory, let's consider another really weird scenario that pops up with non-Archimedean metrics. So suppose again we've got some element of a field, we've got a non-Archimedean metric on that field, and say I've got y sitting in an epsilon ball around an element x. Well, if I take some arbitrary z in the epsilon ball around y, then transporting our properties of the non-Archimedean norm over to the now non-Archimedean metric, the distance from x to z, well, that's going to be at most the distance from x to y and from y to z. But the distance from x to y is less than epsilon, because y is in the epsilon ball around x. And the distance from y to z is also less than epsilon. So either way, the distance from x to z is less than epsilon. So z must be in the epsilon ball around x. And we can turn this exact argument around. So, I mean, what we've done is we've taken an arbitrary element of the epsilon ball around y, and we've shown it has to end up in the epsilon ball around x. And by symmetry, we also get that an arbitrary element of the epsilon ball about y is contained in the epsilon ball about x. In other words, both these epsilon balls are equal. So, what does that say? Well, essentially, this says that if you take any ball in a non-Archimedean metric, then every point is the center.
The universe is an infinite sphere whose center is everywhere and whose circumference is nowhere.
Okay, so now let's start to consider some of the analysis that goes on with these metrics. Suppose I had a sequence of integers, 4, 34, 334, etc. And let's look at some of the differences here. So 4 minus 34, if we evaluate this in the 5-adic metric, well, this number comes out to minus 30, so of course it's divisible by 5 once. Its p-adic norm is 5 to the minus 1. We see a similar thing when we do 334 minus 34, except now it evaluates even smaller. And again, if we try now maybe a bigger difference, not terms that are exactly successive, but again we're gonna take the evaluation here, and notice that the way that this sequence is set up, when we take any of these differences, it's always going to end in some string of zeros, and that string of zeros is really going to be determined by the smallest the smaller number of the two. It's going to tell you exactly how many zeros are going to be left there, and hence exactly how many times that thing will be divisible by 5. So in the last example, for 3,334 minus 34, well, it lobs off the 4, and it lobs off the 1, 3, so we know we're going to have 2 zeros, and so its 5-adic evaluation will be 5 to the minus 2. In other words, what this says is you pick some n, which is smaller than m, and you go a sub n minus a sub m. Well, we know that it's completely determined by the smaller of the two. So if n's the smallest index, we know the 5-adic valuation will be 5 to the negative n. And therefore, this doesn't matter what m is. So in other words, we've shown that this sequence is actually Cauchy. In particular, if we notice each of these terms, if one were to multiply it by 3 and subtract 2, well, as you can see in this example up here, 3 times 4 is 12, 3 times 34 is 102, etc. This will always be divisible by 5, and in fact, so with every successive term, it'll be divisible by higher and higher powers of 5. So, taking 5 to the negative n, this tells us then, well, this sequence, 3 times a sub n minus 2, converges to 0, and therefore a sub n must converge to 2/3. So this is, again, something you kind of have to get used to. This seems in our regular Euclidean norm and Euclidean metric, this sequence clearly grows without bounds and it diverges. But remember, the p-adic metrics are measuring things differently. They're measuring things by divisibility. And in this case, this number actually converges to the ratio 2/3. So now, well, we've talked about Cauchy sequences, and one thing that we do, a sort of standard and arguably the nicest way to construct the real numbers out of the rational numbers, is to view them as a set of equivalence classes of Cauchy sequences. Or in other words, you just sort of demand that every convergent of a Cauchy sequence is a real number, and you kind of fill in those gaps. So one could ask the same thing. Well, what happens if we create a completion of the rational numbers with respect to this new p-adic matrix? And so we're going to define the field of p-adic numbers with its analytic completion to be, well, just that, and denote it q sub p. The proof is entirely similar to the proof that this works for the real numbers, and that it ends up giving you a field, so you can just consult that and essentially write some subscript p's, and the same proof should follow through all the same.
So we have these equivalence classes of absolute values up to topology. So we're going to call a prime or a place of a number field. That's what we're going to use to denote one of these equivalence classes. So at least the prime terminology is motivated by the fact that we get an absolute value, and in fact, thus an equivalence class for each of the prime ideals in the ring of integers. We're also going to get one, of course, for each real embedding. So every real embedding we have of our number field into the real numbers, we just sort of take the obvious Euclidean norm. And likewise, we get one for each complex embedding. However, in this case, we're actually going to define it to be the square of the Euclidean norm. And you might be a little concerned because, well, the square is no longer an actual absolute value. It doesn't satisfy the triangle inequality anymore. But the reason we do this is basically just so it makes a product formula work out nicer for us later on. And really nothing's lost by having the square, because we know we could just take the positive square root. It gives us that absolute value back. And in fact, we don't even need that norm. We can still use the square norm
suppose
to
I have
generate
some prime,
the equivalent topology.
Capital P lying over.
So just to make things nicer, we're going to take
base field
this
P
square.
and some element of K, which contains P to the M in its factorization into prime ideals of L. Well, then that P is going to split in L as B to the ramification index, and again, this whole thing is to the power of P. So, if we work through this, and say we tried to take the capital P evaluation of this, well, it's n of capital P to the negative ramification degree multiplied by m. But then, by definition, the inertial degree tells us that n of big P, well, this is just n of P to the power of the inertial degree, and so we can factor that out. But then n of little p, well, this is from what we've written above, given the factorization, this is exactly the little p-adic norm of the element x. And so in particular, what we find here is that if you were to take a norm coming from a prime sitting upstairs in L and you restrict it down to K, it's actually going to be equivalent to the prime that it lies above. And so here we see the motivation for wanting to call our absolute values primes, because there's this tight association here with the prime ideals, and there's some marriage between the analytic and algebraic properties going on here. So if we consider now the completion of our field with a non-Archimedean value, we consider k hat to be the completion with respect to that non-Archimedean value, and suppose that it's also discrete in this case. Well, in this case, we get, if we have a set of representatives S for our quotient, and of course, as we saw, this means our maximal ideal is also principal. Then it turns out that the series starting from some finite negative power and going up to a large infinite power, where of course our coefficients are lie in our set of representatives. Well, it turns out that this series is Cauchy, so in particular represents an element, and in fact every Cauchy sequence has a unique representation of this form, and so this gives us a really explicit way to look at the completion k hat. So in particular, it's worthwhile considering the example of the p-adic field. It says that QP looks like the infinite series, where we start at some finite negative power of p, go up to large positive powers of p, and of course our coefficients are numbers between 0 and p minus 1. And this actually looks a lot like the case of real numbers, so sometimes this is written as q infinity, called the infinite prime, as just kind of flipped around, right? With real numbers, we have representations of the form where we're allowed infinite negative powers to have possibly non-zero coefficients, and meanwhile we only ever go up to a finite positive power, and again our numbers here are between 0 and 9. And so these are kind of interesting, very similar cases. And in particular, though, with non-Archimedean values, we actually get something a lot nicer happening, because in the real numbers, we know that there's non-uniqueness here. We know that 0.9 repeating and 1, these represent the same real number. But our theorem said that, in this case, our Cauchy sequences are actually unique for non-Archimedean completions, in particular the p-adic numbers. So none of these debates among mathematical amateurs would happen if we lived in a world dominated by, say, p-adic analysis. As one sort of interesting feature that also comes out of this is, if we consider the series starting with p to the 0 and going off to infinity, and all the coefficients are p minus 1. Well, this is actually, if we think about this for a moment in terms of real numbers, this is actually just a good old geometric series that can be evaluated with some high school mathematics. So in particular, the nth partial sum is p to the n minus 1 of this series. So if we look at the p-adic evaluation of the nth partial sum plus 1, well, this is just p to the n, and of course the p-adic valuation of that is p to the minus n. So if we were to take the limit of both sides, of course, this would show that as n goes to infinity, the series, the nth partial sum plus 1 converges p-adically to 0. So in other words, Sn converges to minus 1. That is to say, the series p minus 1 plus p minus 1 times p plus p minus 1 times p squared, so on and so forth, actually represents the number negative 1. So in a sense, we can actually do away with talking about negative numbers in the p-adic world. That is, if we look at just the Cauchy series representation of numbers, we can just look at this series instead, and in some sense there really isn't a minus sign going on. So that's another sort of interesting feature of p-adic numbers and in general. In particular, in the field, as a very concrete example, in the 7-adic numbers, if you had 6 and digits simply flying off to left, again, this is in p-adic form, this infinite string of digits going off to left actually represents -1 in the 7-adic numbers. So now we're finally going to turn things back around and look at just a little bit of the algebraic number theory that comes into the mix here. So suppose I had some finite extension of a field K, which was also separable, and that K is already complete with respect to a discrete and non-Archimedean absolute value. Well, then it turns out, actually, that if we define this absolute value, x of L, to be the norm map, the relative norm between the fields, to the power of 1 over the degree of the extension, this actually agrees with the norm of L. And not only does it agree, thus giving us an extension of that absolute value, but it does it so uniquely, and L actually remains complete with respect to this element. And as a corollary then, suppose we had a possibly infinite separable extension. Well, then we actually get a unique extension in this case as well. Simply think about every finite subextension. By this theorem, there's really only one way to extend, and so that's, basically the obvious choice of infinite extension. Then all you need to do is just pick whatever field finite extension that a given element lies in, and take this as the evaluation. Notice, however, in this case, that L may no longer be complete with respect to the extension. So something, of course, as to be expected, does get lost in the infinite case. It turns out if omega is algebraically closed, then its completion will be as well, though. So there's still some very nice structure going on. In particular, turns out, well, the p-adic numbers q sub p are not algebraically closed. So, of course, we want to try and close them. But it turns out that when we take the algebraic closure of the p-adic numbers, it turns out that we actually, unless p is infinity, or we're just getting the real numbers, other than that case, it turns out that we actually lose the analytic completeness again. So then, after we take the algebraic closure of QP, we then have to go back and complete it again with respect to its Cauchy sequences. And in that case, we get a field which is called CP, or the complex p-adic numbers. And so these are to p-adic numbers what the complex numbers are to the real numbers. And in fact, somewhat strangely, it turns out that this field, CP, is actually isomorphic to the complex numbers. But this actually depends on the axiom of choice, and so this isomorphism is far from explicit. It's only true in the abstract. So now if we consider getting back to the case of algebraic number fields, let's consider the completion with respect this time to any norm and some finite separable extension. Then it's going to turn out that there exist finitely many extensions of that original extension to L. And if we let L sub I denote the completion of L with respect to the corresponding extension of absolute values, it turns out we actually get this nice property here where we have an isomorphism between this the tensor of L and K hat and all the completions of L sub I.
Now we come to what I see as one of the crowning theorems of this whole presentation. And it's a theorem of Ostrovsky, which says that the equivalence classes of norms on a number field are precisely represented by the places of K. So if you recall this slide, we have, I said that we have an absolute value coming from all the prime ideals, each of the real embeddings and each of the complex embeddings. It turns out that these are all of the topological equivalence classes that you get, and they're all distinct. So that is the equivalence classes coming from the norms of each of the prime ideals are distinct from each other and distinct from those from the embeddings. The real embeddings are all pairwise distinct. The complex embeddings are all pairwise distinct and, again, distinct from the other possible places. So I think this is just an incredible theorem because here we have this analytic sort of data of norms and this algebraic data of field embeddings and ideals of rings of integers, and yet there's this strong marriage between these two things for any number field. In particular, up to topology, this means the only norms on the rational numbers are the p-adic norms for some prime p, and of course the infinite prime, as we say, just being the standard Euclidean norm.
We also get the so-called product theorem, and this is why I had mentioned before why we wanted to take the square of the Euclidean norm in the complex numbers, just because it makes this theorem work out a little bit nicer. And so it says that for an algebraic number field K, given any element in that field K, if we evaluate the product of that element over all the infinite places, all the normalized places coming from the exact representatives of each of the prime ideals and the real and complex embeddings, then it all multiplies together to equal 1. And to me, again, this is another very beautiful statement. It's all comes back to one sort of unity, one sort of harmony here. In particular, if we, again, think about the p-adic numbers, then for any rational number, this says if we take the product of all the p-adic absolute values, multiply it by the Euclidean absolute value, then this is equal to 1.
So we can prove just the baby case of this. So suppose we have some rational number, positive, negative, and we look at the prime decomposition of its numerator and denominator as such. And suppose we've got some prime which is not equal to any of the p sub I or q sub j. Well, in that case, the p-adic valuation of x is going to be p to the 0, which is just 1. So if we think about this in terms of the infinite product, I mean, this is saying all the primes that aren't involved in the numerator or denominator are all just going to be equal to 1, which means that almost every term, which is to say all but finitely many terms, are equal to 1. And so they really have no bearing on what the product comes out to, and we can see that definitely this will converge, even though it's an infinite product. Now, if we consider the p sub I adic valuation of x, we can see that it's just going to be p sub I to the negative e sub I, and we get a similar relation for the q sub j adic evaluation of x. So then, putting things together, we have the product of all the valuations of x. Well, we pull out the Archimedean, or the Euclidean, absolute value out in front, and since we already saw that almost all the primes are just going to be equal to 1, we're left with these two other products, one ranging over the p sub I, and the other one ranging over the q sub j. Well, the standard Euclidean absolute value of x, that's just going to give us, as we've written above, we've got our p's up top, we've got our q's in the denominator, and looking at our formulas, well, the first product, the p sub i's, that's just going to be the product of all the p's to their subsequent powers. But the inverses of those, because we saw it's going to be p sub I to the negative e sub I. And then similarly, we have for our q sub j valuations, we have these q sub j to the f of j, and those are going to be up top in the numerator. But now if we look at this whole thing, we've got q sub j to the f of j in the bottom for each j, and q sub j to the f of j up top for each j, and similarly for the p sub i's. So all of this will cancel out and will come out to 1. So you can see this proof really takes the mystery away from this theorem, but I still think it's just a remarkable, neatly tidy fact.
So just to tie things up, I'll talk a little bit about where we can go from here in terms of p-adic numbers. So one really interesting theorem is the Hasse-Minkowski theorem, and this says that given any quadratic polynomial with rational coefficients, it's going to have a solution to that polynomial being set to equal 0, if and only if it has a solution in the p-adic numbers, in each of the p-adic numbers for a finite prime, and a solution in the real numbers. So one direction of this is pretty easy. If you already have a solution in the real numbers and in all the rational numbers, So one direction of this is quite easy to see. The rational numbers sit inside all the p-adic numbers and the real numbers, so clearly if we have a rational solution, then we have a p-adic solution for all the p-adic numbers as well as a solution in the real numbers. The interesting part of this theorem is the converse, that says that we can somehow lift our collective solution from all the p-adic numbers and the real numbers to a rational solution. And as one goes on in arithmetic geometry, there is a sort of tendency to try and mimic this theorem through this idea of what are called local to global principles, where we try and take so-called local data from, say, p-adic ways of looking at things and try and lift that to a rational solution. There's also what's called the Kronecker-Weber theorem, and this says that if we have any finite abelian extension of the rational numbers, then it's contained in a cyclotomic extension of the rational numbers. And so this is a really powerful theorem and part of the groundwork for class field theory, which is about classifying extensions of the rational numbers. And in particular, the belief is that somehow the extensions of Q should somehow... the information about what kinds of extensions are possible should already be contained within Q. And one way of going about improving this is through the p-adic numbers.
Finally, it's time to talk about adel. But not this adel, we're talking about the ring of adels. So the idea behind this is, well, we've got all these valuations, and so we consider all of these things going on separately, but why do that? Why not consider everything at once? So we sort of take this ridiculous looking structure and we take the product over all the valuations. So that is, we take the real numbers, which is the completion with respect to the Euclidean absolute value, and then we take this infinite product over all the p-adic numbers for finite primes p. You'll notice, though, that we've got this little hat on top of the product. And the reason for that is we want to be able to do some functional analysis type stuff. We want some sort of compactness results that will allow us to do some integration and make this theory still work out nicely, both algebraically and analytically. So this is something called a restricted product. And what we do here is we demand that for almost all p, meaning all but finitely many p, given some vector of this product of p-adics, the pth coordinate is going to lie in the ring of p-adic integers. And the reason for this is that the ring of p-adic integers, interestingly, is an example of a set which is both open and compact. So that doesn't really happen often outside of pathological situations, but here it's a feature of the theory, and by doing this, this will allow us to do some nice sort of measure theory integration type stuff.
So we can see then that now we've answered a couple of the things. So this is the reverse of the shirt that we had talked about before. So we saw, in particular, we saw the proof that -1 is represented by an infinite string of 6s heading off to the left in the digital expansion in Q7 particularly. We saw that triangles are isosceles in the p-adic numbers. A couple of these other ones in here we didn't really get to, and they're definitely beyond the scope of this talk, but hopefully those are some tantalizing features that will inspire you to keep pursuing this subject. So thanks for watching, and let me know what you think. Let me know if there's any other kinds of videos you want to see more of, and take care.